I'm going to discuss last section of of chapter 2, which is section 2.7. So let me directly go to the PowerPoint slide. Here is the PowerPoint slide. And I should start in here. 7. Okay, so 2.7 sections we are discussing like how to compute percentile, covariance, correlation coefficients, and empirical rule and Chebyshev rule. So if I have a data, from that data, how can we find a specific percentile value? This is what we are going to learn. For example, suppose I have a data like 20, 31, 50, 61, 92, 7, 5, 90, 15, 17, 31, 41, 49, 52, 32, 27, 29, 24, 31, 42, 60, 92, 88, 88, 54, 64, 61, 69, 42, 77, 71, 79, something like that. So these are the data I have. I want to find the suppose 11th percentile value, 11th percentile, 11 percentile value from there. How can I do that? In order to find the 11th percentile value, that means percents of the data fall below a particular number and 89% of the data falls above that particular number. In order to do that, we have to arrange the data in ascending order. So in order to arrange the data in ascending order, I have to put here 5, and then I have to put here 7, 5, 7. After 5, 7, then I can go to the 15. I can go to the 15, and then I go to the 17, then go to the 19, then go to the 20. After 20, I want to go to the 24. After 24, I want to go 27, 24, 27, 31, 32, 31 and 32. And then again, I have 31. I have 31, and then I have 32, and then again another 31, another 31. There is a 29 in here. There is a 29 in here. After 29, then I need to go to the I need to go to the 41. I need to go to the 41. After 41, I need to go to the 42, 42, 42, 42. And after 42, I'll go to the 49, 50, 49, 50, 50, then 52, then 52, then 54, after 54, then 60, 61, 61, then 60, 61, 61, 64, 69, then 71, 79, 77, 79, 88, 88, 82. These are now I want to find 11 observations, right? In order to 11 observations, I want to find 11 positions. 11 positions so that 11% of the data for okay. In order to find that, this is the formula that we have to put P 100 and 1. P100 and plus 1. N equal to what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So our N equal to 31 plus 1. So it is equal to 32 and P equal to 11 divided by 100. Okay. So now let us find the value. So let us find the value. Where is my R? My R is in there. 11, 11. Okay, 11 times 11, 32 and divided by 100. 3.52%. So we have to consider 3.52%. So third positions 3.52. Okay. Now this is the 15 plus 52. And then this is the formula that I want to mention. Yeah. This is the third position is this 5 to 17 minus, so 50 plus 0.52 times 2, 15 plus 0.5 times 2 equal to 16.0. 16.04. So this is the 11 positions. Okay. So let me do these things by saying these things. If you have a data, for that data, if you are asked to find any percentile value for which that specific percentile number of values fall, and above that for specific number of uh, like if you are asked to find a 77th percentile, you have to use this formula. You have to use this formula in order to find that value. Okay, and then after finding that value, what is the decimal point? That decimal point you will multiply by the difference of the next percentile value from the previous percentile value. This is what is done in here. For example, in this data, if we want to find the 85th percentile value, so we've put the 85 divided by 100, and then there are 12 observations. 12 plus 1 equal to 13. I got the 11th. So 11th is 1 2 3. This is the position 11th which I took in here. This is the 11th positions, and then decimal fraction is in here, will be the difference between the next percentile value and the percentile value that we are looking. So difference of that. So this is the 85 percentile value. So after this, we want to compare quartile. There are quartiles in the data set. That is known as first quartile, below which 50% of the data fall, and above which 75% of the data fall. There is a second quartile, below which 50% and above which 50%. There is a 75th percentile, below which 75% of the data fall, above which 25% data fall. So after this, now we can find the quartiles value. See, 25th percentile value is computing like this, so 3.25, and 75th percentile value is computed 75 over 100, 25 plus 1, so 9 point this. So now they are now computing a specific value. So this is the third percentile value, 138. 138, take a look at that. 138, third 138, this is the third percentile value. This is the third percentile value. This is the third percentile value, and this is the difference between next to the third percentile and third percentile value, and multiplies by the decimal fraction. So this is the 25th percentile value, that is the 75th percentile value, and the difference between first quartile and third quartile, difference between third quartile and first quartile is known as the interquartile range. So we have computed that way. Why we compute these things? When we want to construct the box plot, any data, suppose this is the data is given to you. This is the data given to you. And for this data, you are asked to construct box plot. So in order to do what you are going to do, you will do this. So this will be in the scale. So scale, this will be Q1, 25th percentile or first quartile, and then you will compute here second quartile. Again, this will be scale. This would not come exactly in the middle. Okay, this will not come exactly in the middle. And this is your scale. Like here, you can put here 0, 5, 10, 15, 20, 25, 30, 35, and 40. This is the scale. And this is where your Q1 is. This is where your Q2 is, sorry, Q3 is, which is equal to 75th percentile, which is equal to 25th percentile, and then suppose this is your median Q2, which is equal to 58th percentile. Okay, after constructing this, now you have to construct whisker. How can you construct the whisker in order to compute box plot? Remember, I Q R, which is interquartile length Q3 minus Q1. Now, lower inner lower inner fence is computed Q1 Q1 minus 1.5 IQR. Okay, lower inner fence, and then upper inner fence, which is known as the Q3 plus 1.5 times IQR. Lower inner fence and upper inner fence. Lower inner fence and upper inner fence. These things is done. So we can compute this. We can compute these values is in here. Lower inner and upper inner fence, these two values will be considered in here. Suppose I want to get it in here, suppose lower inner fence 2.17. Okay, and that one suppose I got 30. Suppose I got there 83 point something. If, or maybe I can write here according to that scale. I can write here. Suppose I got here 36.2. Okay, now we have to construct the whisker. We have to construct the next line to the maximum within the upper inner fence, within the upper inner fence. So I have to drag it to the data point where the data point is to the upper inner fence. Upper inner fence is what? Upper inner fence is 36.2. So 36.2 in, suppose 36.2 is in there, right? Like this. This is 36.2. 36.2. So I can drag this line. Let me erase this time. Now you will understand. Drag this line to the maximum within the upper inner fence. Suppose maximum within upper inner fence, the maximum value is 35.5. So that means 35.5 is in here. I have to stop in here. Drag this line to the maximum of the data within the upper inner fence. Drag this line. Suppose lower inner fence is 2.7. And then maximum of the data within this 2.7, maximum of this data is suppose 3. So drag this whisker to the minimum of the data point within the upper inner fence. The minimum of the data is suppose 3. This has been the stop. But upper inner fence is 2.7. 2.7 could be in there, but I have to drag it in there with the drag this line to the minimum of the data within the upper inner fence. Okay, let me write these two things so that you can understand. Draw the line whisker to the maximum of the data within upper inner fence. Draw the line whisker to the minimum of the data within lower inner fence. So this is the way you need to understand these things. Draw the line whisker to the maximum of the data within the upper inner fence, and draw the line whisker to the minimum of the data within the lower inner fence. Okay. Any data that falls beyond this is known as the outlier. Okay. So far what we learned to compute any percentile values, how to compute 25th percentile, which is first quartile, 50th percentile, which is second quartile, 75th percentile, which is third quartile, and how to construct box plot. If the variable is quantitative variable, always draw box plot and histogram side by side. From there, you can easily take decision on eight statistical measures. These are known as the model class, type of the frequency distribution, whether it is skewed to the right or skewed to the left, or it is symmetric. And the remaining 6 decisions you can take from the box plot: minimum, maximum, first quartile, second quartile, third quartile, and outlier. So these 8 measures, statistical measure, you can find when you draw box plot and histogram side by side. Okay. I think these are the discussions about. Okay, now I want to construct the z-score. Okay, before going to the z-score, which we will discuss in depth when normal distributions will be discussed. But here, I just want to discuss the empirical rule and Chebyshev rule. So what is empirical rule? Insert. So okay, if you have a quantitative variable and if you draw the histogram and add the top middle point of each bar, and then that smooth frequency curve look like symmetric, so that means 50% of the middle side, right side, 50% in the left side, then this curve is known as the bell shape because it look like bell. It called mound shape, or it is called the symmetric curve, symmetric curve, or normal curve. Okay, normal curve. So now I want to draw something. Suppose this is my mean, and which is equal to suppose 10. And this is known as the variability. So if variance, if variance is very if variance is very small, then this curve will look like this. If variance is very small, then this line will shrink. It is still normal, but the variance is small, so that is why it shrink. Okay, it shrink. So now you have understand when it become little uh, um, fat compared to the this one which is slim. So if that is like this is spreadness or dispersion, this is called the variability. Okay, if variance is high, dispersion is high, it will spread out. But in this case, suppose our mean x bar equal to 10 and then our standard deviation s equal to 2. Okay, then this is the rule. This is the rule. Within one standard deviation from the mean to the left, within one standard deviation from mean to the right. So that means this is x bar plus s and this is x bar minus s. In this case, remember this curve is constructed from histogram and histogram is constructed from the quantitative data by class interval and frequency. Then within one standard deviation, because if you subtract standard deviation from mean in here and if you add standard deviations from mean in here, within one standard deviation in this part, 68% of the frequency fall, 68% of the data fall. Now if you come to the second one, x bar minus 2s, and then if you do this here, x bar plus 2s, x bar plus 2s, এটা যদি like x bar plus 2s, then in such a cases 95% of the data fall. 95% data fall. And within three standard deviation, x bar minus 3s, within three standard deviation, x bar plus 3s, okay, so take a look at this. If you have a quantitative variable, from that quantitative variable, if you construct a frequency table with class interval and frequency corresponding to that class interval and construct the histogram and then add middle point of each bar the frequency curve that if we look like a symmetric curve, then within one standard deviation from mean, 68% data fall. 68% of those frequency fall, 68% of those data fall. Okay. And then within two standard deviations, 95% of the data fall. 95% of the okay, and within three standard deviations 99.7% of the data fall. That is what known as the empirical rule. Now the question is the question is I want to find in on five standard deviation. I want to find in 2.3 standard deviations. So that means x bar within x bar plus 1.7 standard percentage of data fall. X bar plus 0.95 standard deviation. How can we find those things? That answer could be done by reviewing normal distribution. No distributions that done by normal distribution. Normal distribution. Okay. Now, which we going to discuss in another class. Now, after doing empirical rule, now I want to do Chebyshev rule. I want to discuss Chebyshev rule. Suppose your frequency curve does not look symmetric. It looks to the right or skewed to the. In such cases, what percentage of data fall within one standard deviation? What percentage of data fall within two standard deviations? That answer could be given by using this formula. Within one standard deviation from mean, no useful information. No useful information. But within all other um, standard deviations from mean, so the instead of within a standard deviation from mean, 1 minus 1 over k square of data false. So let me give a specific example. Suppose k equal to 2. Suppose k equal to 2. So standard deviation, what percent for 1 plus 2 square three over 4, which is equal to 75%. So within two standard deviations, 75% of the data fall from the mean. Okay. So more specifically, if your data like this way, it is going like this way, like this. And as I said, this is the mode. Okay. And this is the mean, right? So this is the median. This is the median. This is the mode. This is the mode. And this is the mean. Mean, which is equal to x bar. Okay. So if you go like this way, x bar plus 2s and x bar minus 2s, x bar minus 2s, x bar minus 2s. So that means within two standard deviation from mean in this area, within this 75% of the data fall. Similarly, the explanations for the skewed to the left. Now, if I want to do this way, skewed to the left, same rule will be applied. So within k standard deviations, 1 minus 1 over k square percents of data fall when your frequency curve is skewed to the left or skewed to the right. And this rule is known as the Chebyshev rule. Chebyshev rule. Okay. And that rule is known as the empirical rule. Empirical rule. Okay. After this, now I'm going to discuss empirical rule. I have discussed identifying outlier. I discuss box plot, discuss how to construct box plot. Let me tell you, constructing box plot and histogram using Excel is very tough. Okay. I therefore provided you the R code. in the exam or quiz, if you need R code to construct box plot or histogram during the exam, I can provide that, or I will provide the code already in the video, and by email I can also provide you, so you can use the open R and construct these things. If I want to construct the box plot the way they have described in here, it will be just a waste of 30 minutes from my life, so I don't want to go there. Okay, so scatter chart. Okay, now the two more things. Scatter plot means if in x-axis, if you put one variable and y-axis you put another variable and then show the scatter plot, then you will get the scatter plot. Let me see if I can do one scatter plot from the data. Let me see. Soft drinks is a death. Mm, mm. So, okay, let me quickly show you scatter plot by using R, empty cars data. And then if I want to plot empty cars, dollar sign, MPG, MPG, empty cars, dollar sign, DISP. So if you hit like this way, this is the scatter plot. One is going up, another one is going down. So DSP is going down, the MPG is going down, and MPG is going up, and then DISP, maybe dispense this DISP uh, will go is going down. So this is the scatter plot, and same thing I think we can do in Excel by opening a data. Let me see if I can open a data desktop. Mm. It's just one variable data. I want a data that will have a two variable. Mm. Okay, let me do quickly construct a data. A, B. So 10, 15, 13, 12, 18. Oh my goodness. 15. So this is the scatter plot. Okay, you have seen scatter plot using both. You have seen scatter plot using both R and Excel. Okay, now let me more things, then we are done. Okay, so another thing we want to do now is called the covariance. So let me do these things by covariance. What is the pen? So covariance means joint variability. Covariance is computed like this way. Suppose there are two variable x1 and x1, x and y. X has a value like 2, 3, 4, and y has a value like 5, 6, 7. Then what you will do? X minus x bar and then y minus y bar. You compute these things. So 9 divided by 3 average equal to 3, and 18 divided by 3 equal to y bar equal to 6. Now you can find here 2 minus 3 equal to minus 1, 3 minus 3 equal to 0, and 4 minus 3 equal to 1. Then 5 minus 6 equal to 1, and 6 minus 6 equal to 0, and 7 minus 6 equal to 1. So now if you want to multiply this x minus x bar and y minus y bar, then you will find it in there in this format. This is negative 1, this is 0, this is positive 1. Okay, this is okay, so now if you sum them up, you will get 0. Sum them up, you will get 0. So now the definition of covariance written as covariance of x comma y, that is computed 1 over n minus 1 sum of xi minus x bar and yi minus y bar. So my sum of xi minus x bar here is 0. So the covariance is 0. So this is the way to compute covariance by using paper and pen approach, but covariance could be covariance could be, as I have computed here, as I computed in here, covariance of x comma y, which is equal to 1 over n minus 1 sum of xi minus x bar and yi minus y bar. And then in such a cases, you will get covariance value could be positive. You will get a positive value. Okay. You will get a 0 value and you will get a negative value. If covariance value is positive, two variables are positively correlated. So that means one increases, other increases. If covariance is close to 0 or 0, that means there is no relationship between variable, because changes of one variable would not affect the change of other variable. If covariance is negative, then changes in one value would changes is one value would cause changes in another value in opposite direction. Increase one variable would cause another variable to decrease. So covariance could be positive, could be negative, could be 0. But from the covariance, limitation of the covariance is that it cannot tell how strongly, or it cannot tell how strongly or weakly two variables are correlated. Two variables are correlated. It cannot tell how strongly or weakly two variables are correlated. In order to do that, we need to compute correlation coefficient. In order to tell that two variables are uh, strongly correlated, strongly positively correlated, or highly positively correlated, or fairly positively correlated, or two variables are highly negatively correlated, or perfectly negatively correlated, or weakly negatively correlated. Another measure known as the correlation coefficients. Correlation coefficients need to be computed. What is that? Correlation coefficient is usually denoted by R, X, and Y, and its formula is covariance E of X and Y that I defined above, divided by S of X and S of Y, where this is a standard deviation of variable X, this is a standard deviation of variable Y, this is a covariance of X and Y. And more specifically, if someone asks me to write their formula, you can write like this: so sum of xi minus x bar, yi minus y bar, and sum of xi minus x bar square, and sum of yi minus y bar square, and square root of this. Okay, this is the formula for computing correlation coefficient. Now, correlation coefficient has the highest value of positive 1 and lowest value of negative 1. And if there is a value of 0, two variables are not correlated. If the value is 1, then x and y are perfectly correlated. X and y are perfectly positively correlated. If this is what, then x comma y are perfectly negatively correlated. Okay, and then if they is like, if there is a positive 0.90 and above positive 0.90 and above and less than 1, then high positively correlated. If there is a less than negative 0.90, like this way, r value is less than 1 and greater than negative 0.9, then this is called highly negatively correlated. Now if ranges from 0.75 to 0.90, then fairly positively correlated. If it is negative 0.90 to negative 0.75, then it is called fairly highly correlated. And if it is between 0.50 to 0.75, then moderately highly correlated, highly positively correlated. If it is between negative 7 and negative 0.50, moderately negatively correlated. And below zero point 0.5, the correlation is weakly correlated, weakly positively correlated, weakly negatively correlated. Okay, these are the all discussions about correlation coefficients and everything. How can we find correlation coefficient using using R and Python? So let me go there. So our data is head. Our data is head empty cars. And then if you want to write COB, covariance of empty cars, dollar sign, MPG, empty cars, dollar sign, DR80 red, then we got this. This is the positively correlated, but if I want to find the correlation of them, I just need to find like this, COR, core. So correlation is this. So that means they are moderately highly positively correlated. Okay. The two variable MPG and DRET are moderately highly positively correlated. Now, if I want to do the opposite direction one, let me do it by DISP and then MPG. Are you seeing negative? The figures that we had scatter plot, it was showing similar, right? So if you plot in here, see the one going up, another going down plot. Are you seeing? So when DISP is up, MPG is in here. One is up, another one is down. And now MPG is high, DISP is low. So one is going up, other is going down. So are you seeing? This is the trend. Now there is a way to compute correlation coefficient in Excel. So, okay, so let me find the covariance. I want to do covariance. I want to do covariance. And then I want to put the two values in there and then hit enter. What? Array 1 and array 2. Okay, I have to put here array 1 and array 2 and then hit enter. So this, okay, let me change it. So covariance, I have to come in here like this, and then I have to come in here like that and like this. Array 1, then array 2. Here is the covariance. Now, if I am asked to find the correlation, so I just need to change it here. Just come here, change it to correlation. And okay, let me get rid of these things completely. Coral. And then this. So this is the correlations between two variable A and B. Okay. So that's it. And next class, we are going to discuss about normal distributions. So let me stop in here, stop recording.